This lesson is on implicit differentiation. Up until now, when we have found the derivative of a function, the function has been defined explicitly, meaning we could write it as y equals something that is a function of x only. So the terms on the other side of the equal sign were some combination of x's and functions of x's and constants. Implicit differentiation is used when we know y is a function of x, but it's not defined explicitly. We don't know exactly what it is. We can't write it in terms of y equals. And so since we don't know exactly what y is, we don't know exactly what its derivative is, and we just write it as dy dx. An equation that looks like this would be x squared minus 2y cubed plus 4y equals 2. If I wanted to take the derivative of this explicitly, I would need to solve for y and then take the derivative of both sides. But I cannot solve this equation for y and get it by itself. Now let's just look at the y cubed. If I wanted to take a derivative of y cubed, knowing that y is a function of x, I just don't know what it is, that makes this a chain rule problem. And the derivative of the outside function would be 3y squared times the derivative of the inside function, and we don't know exactly what it is, we just write that as dy dx. So when we're solving this type of equation, there are some guidelines to follow. We differentiate the entire equation with respect to x. Since we're solving for dy dx, we want to put any terms that have that on one side of the equal sign and terms that don't involve it on the other. Factor out the dy dx if need be, if there's more than one term with it, and then solve for it. So let's see what an example of this looks like. Okay, so if I want to take the derivative of this equation that is defined implicitly, I cannot solve for y by itself, I'm going to take the derivative of both sides with respect to x. And on the left-hand side, well, when I take the derivative of x squared, that's just the way we're used to doing it. We're going to get a 2x. When I take the derivative of negative 2y cubed, the negative 2 stays out front. And we just did the derivative of y cubed. It's 3y squared times a dy dx, because it's a chain rule problem. And for the 4y term, we keep the 4, and the derivative of y is dy dx. And the derivative of 2 is 0. So this means I can subtract the 2x from both sides because it doesn't have a dy dx attached to it, and we end up with negative 6y squared dy dx plus 4 dy dx equals negative 2x. And now I can factor out these dy dx's so I can get it by itself and solve for it. So I get dy dx times negative 6y squared plus 4 equals negative 2x, and then I can divide both sides by negative 6y squared plus 4. And if I factor out a 2 from the denominator, I can simplify this and end up with negative x over negative 3y squared plus 2. Let's try another one. Okay, we want to take the derivative of both sides. So I'm going to put a d dx in front of both sides, which is the command telling me to take the derivative. And when we do the y cubed, we get 3y squared times dy dx, because anytime we take a derivative of a y term, we're going to put a dy dx on it because of the chain rule. Derivative of y squared would be 2y times a dy dx. Derivative of negative 5y would be minus 5 dy dx. The derivative of negative x squared would be negative 2x. And the derivative of negative 4 is 0. So we're going to add 2x to both sides here. And I have 3y squared dy dx plus 2y dy dx minus 5 dy dx equals 2x. And we will factor out the dy dx's, leaving me with 3y squared plus 2y minus 5 equals 2x. And we'll divide both sides by what's in the brackets. And we get an answer that cannot be simplified. So this is equal to our dy dx. Okay, let's take this a step further. In this example, I'm going to find the derivative implicitly, and then I'm going to evaluate it at the point 3, 1, which means at the end, we will plug in a 3 for the x and a 1 for the y, because these derivatives are in terms of x's and y's, not just x's anymore. So we're going to take the derivative of both sides of this. And this is a pretty complicated derivative. On the left-hand side, I see chain rule. On the right-hand side, I see product rule. So on the left-hand side, I have 3 times something squared is going to become 3 times 2 times something to the first power. Let me put that inner function back in, times the derivative of the inner function, which would be 2x plus 2y, and we need a dy dx there, equals, on the right-hand side, let's make 100x be our first function. The derivative of 100x is 100 times the second function plus 100x times the derivative of the second function would be dy dx. Now, in order to separate out my dy dx's, I've got some algebra to do. So I am going to distribute on the left-hand side. So if I multiply by these terms separately, I'm going to get 12x times x squared plus y squared plus 12y times x squared plus y squared dy dx. still equal to 100y plus 100x dy dx. And now I see my dy dx terms separately. I want to get them on the left-hand side of the equal sign and get the terms without dy dx on the right-hand side. So that's my next step. I'm going to subtract this term from both sides and this term from both sides. When I do that, I end up with 12y times x squared plus y squared dy dx minus 100x dy dx equals 100y minus 12x times x squared plus y squared. If we factor out our dy dx's, I end up with dy dx times 12y x squared plus y squared minus 100x equals 100y minus 12x times x squared plus y squared, and we'll divide both sides by what's in the brackets. So this one's pretty messy. And so I can write my dy dx. If I factor out a 4 from both the numerator and the denominator, it will simplify it a little bit. And so those will go to 1. And then we want to evaluate this at the point we were given, 3, 1. So let's just write the simplified version. So that means in the notation for evaluate at is this vertical line with the values that we want to use for our x and our y. And when we plug those in, y is 1. I get 25 minus 9 times 9 plus 1, x is 3, over 3 times 9 plus 1, minus 25 times 3 is 75, gives me 13 over 9, which meaning-wise would be the slope of the tangent line to the curve at the point 3, 1.